Hello everyone, welcome back. So, let us continue our discussion. This is week 4 and we are in the first lecture. Today, we are going to learn plane stress problem. Now, before we go into the details of plane stress, let us first go back and review what we have done with a 3D stress field. Now, the 3D stress field that we used in the last week and derived different expressions is defined by this matrix, right. And we are familiar with how to find out the traction acting on a plane which is defined by its direction cosines nx, ny and nz, right. So, this is what we are familiar with. So, Tx, Ty and Tz. And we have also discussed the principal value problem. Now, using this expression, we can find out the tractions Tx, Ty, Tz, and we can also find out the principal values or principal stresses. Now, there are 3 principal stresses: sigma 1, sigma 2, sigma 3. And for that, we can also draw the Mohr circle. Fine. Now, there are some problems where we have a special case sigma zz equal to 0, tau xz is equal to 0, tau yz is equal to 0. So, this is a special case. If you look at the notation, what it means? It means all the stress components along z direction are 0. So, what is the situation? We have, say, a thin plate and we have all in plane loading, right. Say there can be any other type of loading, but all of them are acting in plane. Similarly, on this face also we can have some loading. What are the examples? You have seen bridges where very often we use plates. So, steel plates having in plane loading is an example where we have all stress components along z direction is R0. If this is the case, we call it case of plane stress, right. Now, if we have a plane stress problem, then as per our definition, sigma zz goes to 0, sigma yz goes to 0 and xz goes to 0. So, effectively we have a two dimensional problem. So, Tx and Ty is given by sigma xx tau xy sigma yy, and then we have nx and ny. So, it is a 2D problem. Now, the question is, for 2D problem we have already derived the expression for sigma n and tau n. So, what we will do today is we will revisit those expressions, but our starting point is this expression here. So, we will start from 3D, we will apply the conditions as a special case and we will try to derive those expressions and we will see whether we get the same solution or not. Now, if we start with this expression and then obviously we have sigma n in terms of Tx and Ty. So, we can easily write Nx times Tx plus Ny times Ty plus Nz times Tz, but because we have no z component obviously we can neglect the third term, and this is the expression for sigma n. In this expression what we can do, we can put the expression of Tx and Ty. So, if we do that, what we will get is Nx times Tx, which is sigma xx Nx plus tau xy Ny, then we have to add Ny times Ty. So, in place of Ty we can write tau xy times Nx plus sigma yy times Ny. Right. Then let us expand this. So, we have Nx square sigma xx plus Ny square sigma yy, and then we have Nx Ny times tau xy and it appears twice. So, we have 2 times Nx Ny tau xy. Fine. Now, what is Nx? In 2D, this is cos of alpha x, and what is Ny? Ny is equal to cos of alpha y. And what is the interrelation between alpha x and alpha y? Alpha x is equal to 90 degree minus alpha y. So, we can write this as sine of alpha x. Now, if alpha x we write only one angle because it is in 2D, other one will be 90 degree minus alpha. So, this is cos alpha and Ny is sin alpha. Then, if we modify this expression, so we have sigma xx cos square alpha plus sigma yy sin square alpha plus tau xy times 2 into sin alpha cos alpha, and this is exactly the expression we derived earlier. We can further simplify. If you recall, cos square alpha is equal to half 1 plus cos 2 alpha, and sin square alpha is equal to half 1 minus cos of 2 alpha. And if you use this expressions, then we can further simplify. We have sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 times cosine of 2 alpha plus tau xy sine of 2 alpha. So, we have sigma n, and that we earlier derived using a triangular wedge, and we applied equilibrium equation, if you recall, when we discussed 2D. And right now, we derive the same expression starting from this 3D expression of stress field, and then we apply the special case for plane stress condition. So, we get sigma n, and obviously, we can review whether we get the same expression that we derived for tau n. Okay, so let us derive the expression for tau n, right. So, tau n, right. For that again, we already have the expression for Tx and Ty. So, we know Tx, Ty is equal to sigma xx tau xy sigma yy times direction cosine nx and ny. Okay. Now, t is equal to again, or t square equal to t x square plus t y square, and tau n square is nothing but t square minus sigma n square. So, the expression for sigma n we have already again derived. Sigma n is equal to sigma xx nx square plus sigma yy ny square plus tau xy 2 times nx ny. Okay. So, in this expression, then we can write Tx square and Ty square. So, that will be sigma xx nx plus tau xy ny whole square plus we have tau xy nx plus sigma yy ny whole square, then minus we have sigma xx nx square plus sigma yy ny square plus tau xy 2 times nx ny whole square. Right. So, what we will do next is we will simplify this expression. For that, we have to open these brackets, and then if we do one by one, we have sigma xx square nx square plus twice nx ny, and then we have sigma xx tau xy plus we have ny square tau xy square, then plus, if we open the bracket for this second term, we will have nx square tau xy square plus twice we have nx ny, and then sigma yy tau xy, and then the last term from this second term in the first line, we have sigma yy square n y square, then minus we have n x to the power 4 sigma xx square plus n y to the power 4 sigma yy square plus we have 4 nx square ny square tau xy square, then plus we have twice nx square ny square, and then sigma xx sigma yy, then plus 4 times we have nx cube ny, and then sigma xx tau xy, plus 4 times we have nx in y cube, and then sigma yy tau xy, right. So, that is the complete expression. Now, we can open this third bracket. Obviously, all this will be negative. So, all of them have negative sign, right. Now, you can see we can further simplify. So, for that let me first show you. Here we have ny square tau xy square, and then next term is nx square tau xy square. So, if you recall the properties of direction cosine, nx square plus ny square is equal to 1. Because we have 2 dimensions, we have only nx and ny. Then we can also further simplify. For example, if you consider this one and this one, what we will get? We will get sigma xx square nx square common. So, within bracket we will have 1 minus nx square, and that is ny square, right. So, what we have sigma xx square, then nx square ny square. Okay. So, this term gone, these two, and we have also considered tau xy square. Similarly, we can consider this term and this term. So, what we have is sigma yy square, and again if we take ny square common, so we will have 1 minus ny square. So, that is nx square. So, we will have here nx square ny square, and then plus tau xy square that I have already explained. Okay. Then what next? So, we have plus we have twice nx ny, and then sigma xx tau xy, right. So, this is the term, plus we have twice nx ny, and then sigma yy tau xy. So, here is the term. Then we can further simplify. So, what we have here is, say, these term and these term, right. So, let us write it down. So, minus we have 4 nx cube ny, and then we have sigma xx tau xy, then minus 4 we have nx ny cube, and then sigma yy tau xy, right. And the remaining terms we have is this one here and the next term. So, let us write it down, minus 4 nx square ny square tau xy square, minus twice nx square ny square sigma xx sigma yy. So, this is the last term we have considered, right. Now, if you recall, nx is equal to cosine of alpha and ny is equal to sine of alpha. So, at this stage let us introduce, because we will see whether we get back the term that we that we derived earlier. Okay. So, what we have here, sigma x x square, then cos square alpha times sin square alpha plus sigma y y. We have cos square alpha times sin square alpha plus we have tau x y square, right, and then we have twice cos alpha sin alpha sigma, the first term sigma x x, and then tau x y. Okay. Then we have plus twice cos alpha sin alpha sigma y y tau x y, then minus 4 cos cube alpha sin alpha sigma x x tau x y minus 4 cos alpha sin cube alpha sigma y y tau x y. Then the last two terms, 4 cos square alpha sin square alpha tau x y square, then minus twice cos square alpha sin square alpha sigma x x sigma y y. Now, again we will further simplify. What we can see is, say, this term we can take 1/4 common. So, what we will have, sigma x x times sine of 2 alpha whole square divided by 4, right. Similarly, this term we can rewrite 1/4 sigma y y sine of 2 alpha whole square. Then we will consider this term here. So, we have minus then half, we have here sigma x x sigma y y and then sine square 2 alpha, right. Then we have this term, and here we have sigma x x tau x y, right. So, what we will do, plus sigma x x tau x y, and then we can further simplify. Actually, there will be alpha here. So, sine of 2 alpha, then within bracket 1 minus we have 2 cos square alpha, right. Okay. Then we have other terms. So, what we can do, we can take sigma y y tau x y common. So, we have sigma y y tau x y times sine 2 alpha, within bracket we have 1 minus 2 cos square alpha, right. Then we have here tau x y square, and then we have another one here tau x y square. So, plus tau x y square, and then within bracket 1 minus sine square 2 alpha, right. Okay, we are almost there. So, let me write here. So, tau n square, what we get, you can see if we consider these three terms, then we can write it in a compact form sigma xx minus sigma yy by 2 times sine 2 alpha whole square, right. Then we have the next two terms. Here we have sine 2 alpha 1 minus 2 cos square alpha. So, this will be cos of 2 alpha, right. Similarly, here also we have cos of 2 alpha, right. Let us write. So, we have minus, if we write sigma xx minus sigma yy by 2, then we have 2 times sine 2 alpha cos 2 alpha, right. And then the last term we have tau of xy square, we have cos square 2 alpha, right. So, I think just 1 minute, let us check once more. So, here if you check the term, here we have tau xy. So, there will be a tau xy here. So, let me rewrite this term once more. So, we have minus 2 times sigma xx minus sigma yy by 2 times tau xy, because we have tau xy here, right. Okay. So, then we can further simplify this expression, which is sigma xx minus sigma yy by 2 sine of 2 alpha. Actually, this is a square minus 2ab plus b square. So, it is a minus b or b minus a. So, let us write either way. So, a minus b or b minus a whole square. So, let us write it accordingly. So, this is square of this third bracketed term, right. Now, you can see what we have here is the expression for tau n. So, for tau n, we have minus sigma xx minus sigma yy by 2 sine of 2 alpha plus tau xy cos of 2 alpha. So, now the derivation is complete. Again we get the same expression that we derived earlier for tau n, but this time what we do? We started with the 3D stress field and then we applied the condition for plane stress, and again we get the same expression. So, that actually completes our derivation that we wanted to check. So, the same expression we get from the 3D stress field, right. Okay. So, let us continue further. Now, for this plane stress problem, let us again revisit the same path and see whether we get the same expression for eigenvalue problem, right. So, for that again we have Tx, Ty, which is sigma xx, tau xy, and then sigma yy times we have the direction cosines nx and y. Our objective is to find out the principal stresses. So, it is sigma and sigma. So, that is the 2D stress field, and for the same direction cosine we have nx and y, and this should equate it to the traction Tx and Ty. So, if that is the case, then what we have? We have again the same eigenvalue problem. So, sigma xx minus sigma, then tau xy, then we have sigma yy minus sigma times nx and y is equal to 0. Now, for the trivial solution nx equal to ny equal to 0, that what we are not looking at. So, inverse of this matrix should not exist, and for that we have the condition sigma xx minus sigma then tau xy, and we have sigma yy minus sigma, here again tau xy is equal to 0. If that is the case, we can find out the quadratic equation, because we have a 2D problem. Obviously, this time we have quadratic equation sigma xx minus sigma times sigma yy minus sigma minus tau xy square. So, if we simplify it further, we get sigma square minus sigma xx plus sigma yy times sigma, and then plus sigma xx sigma yy minus tau xy square. Now, for 3D problem, if you recall, we had 3 stress invariants. The first one is sigma xx plus sigma yy plus sigma zz. I2, the second invariant, is sigma xx times sigma yy plus sigma yy times sigma zz plus sigma zz times sigma xx minus tau xy square minus tau x z square minus tau yz square. And then the third invariant, that is the last invariant, we have sigma xx sigma yy sigma zz plus 2 times tau xy tau yz tau zx minus sigma xx tau yz square minus sigma yy tau xz or zx square minus sigma zz tau xy square. So, these are the 3 stress invariants. Now, if you look at the special case that we studied today, so special case is sigma z is equal to 0, tau xz is equal to 0, tau yz is equal to 0. So, if that is the condition, then what we have? This is 0, then here it is 0, this quantity is 0, and these two are 0. And all the components in I3, because they contain the stress components along z direction, all of them are 0, because here it is 0, here these two components are 0, it is 0, here it is 0, and here it is 0, right. So, I3 is equal to 0, and this is basically the condition for plane stress problem. Okay. And if you look at the expression, the remaining term, we have sigma xx plus sigma yy, what we get here, and the second invariant, we have sigma xx sigma yy minus tau xy square, right. Again, what we get is the most important condition is that the third invariant is 0 for plane stress condition. Now, what we can do, we can find out the roots of this equation. So, for that we have minus b. So, we will have sigma xx plus sigma yy plus minus then square root of b square. So, we have sigma xx plus sigma yy whole square minus 4 times 1 times we have sigma xx sigma yy minus tau xy square divided by 2. Obviously, we can open the bracket here. So, if we do that, what we will have is 4 times sigma xx sigma yy plus 4 times tau xy square. Now, if we consider this term minus 4 times sigma xx sigma yy. So, what we have sigma xx plus sigma yy square minus 4 times sigma xx sigma yy. Obviously, we can take this term inside. So, what will happen is this will be minus, right. So, we have plus 4 times tau xy square. We can further simplify this. What we get sigma xx plus sigma yy by 2 plus minus, then we take this 2 inside. So, what we will have sigma xx minus sigma yy by 2 whole square plus tau xy square. Again, if you look at this expression, so we have sigma 1 2, that is we have in this case 2 principal stresses, and this is the expression again we derived for the 2D problem, and we again get the same expression. So, what we have here is sigma 1, which is the first principal stress, and sigma 2 is the second principal stress. Now, finally, what will be the equilibrium equation for plane stress problem? Now, if you will recall the equilibrium equation for 3D, it is sigma xx differentiated with respect to x plus tau xy differentiated with respect to y plus tau xz differentiated with respect to z plus gamma x is equal to 0. That is the first equation. Then we have tau xy differentiated with respect to x plus sigma yy differentiated with respect to y plus tau yz differentiated with respect to z plus gamma of y, and then the last equation is tau xz differentiated with respect to x plus we have tau yz differentiated with respect to y plus sigma zz differentiated with respect to z and plus gamma z. So, this is the last equation. So, we have first, second and third equations of equilibrium when you consider the 3D problem. Now, in this case we have plane stress. So, this entire equation is not required. So, this entire equation, and obviously these terms will not be there. So, for plane stress problem, if we write down the equilibrium equations for plane stress problem. So, we have sigma xx differentiated with respect to x plus tau xy differentiated with respect to y plus gamma x equal to 0. Then tau xy differentiated with respect to x plus sigma yy differentiated with respect to y plus gamma y is equal to 0. So, these are the two equations. So, this is say 4 and 5. So, this two equations, they are for 2D case as we have in case of plane stress problem, and that completes the derivation. So, if we have a plane stress problem, it is defined by sigma xx, sigma yy and tau xy. Then from this 2D stress field, we can find out sigma n, tau n, then principal stresses sigma 1, sigma 2, and of course, their directions also we can find out, which I am not going to explain for the time being, because we have already derived that. And finally, we have the equilibrium equation for plane stress problem. So, with that, let us close here. In the next class, what I will do, I will solve some problem for you, and then we will see how this plane stress problem helps us in some special cases where instead of considering complete 3D stress field, we can actually consider the plane problem, and that reduces the problem size, and effectively we can solve all the necessary stress components. Thank you very much.